Hi students. This is lecture 2. It's about modeling system and terminology. We are going to visit some important terminology for network simulation or simulation at all in this lecture. Hence, I have updated the PDF uploaded in the model system, so you have to recheck the PDF again. Okay. Modeling and system terminology. The following are some of the important terms that are used in simulation modeling. Let's start with the state variables. The variables whose values describe the state of the system. They characterize an attribute of the system, such as level of the stock in an inventory or a warehouse, or number of jobs waiting for processing. Any variable inside the system, we can assign it as a specific state variable for that system. Any system may have more than one state variables. In the case where the simulation is interrupted, it can be completed by assigning to the state variables the values they held before an interruption of this simulation. For example, if you are going to do a simulation in a computer system and you need to interrupt or pause the simulation for a moment, before that you have to save all the state variable values, and when you want to resume your simulation, you can give back the last values you obtained from the state variables and continue the simulation again. The next term is event. An event is an occurrence at a point in time, which may change the state of the system. Example, the arrival of a customer or start of work on a job. An event is a point in the time of the simulation, which the state have changed somehow. If the system is stable or it's not, there is no under changing in some state variable, then there is no event. Event always happens when something new or change in the system behavior is going on. The third terminology is entity. Entity is the object that passes through the system, such as cars at an intersection, for example. If you have a traffic circle or traffic intersection, or orders in a factory. Often events, example arrival, are associated with interactions between one or more entities, example customer and store. With each entity have its own state variables. Example, customers have cash and stores has inventory. The fourth term is a queue. You are familiar with a queue. A queue is a linearly ordered list. It's a list. A physical queue of people, for example, a task list, a buffer of finished goods waiting for transportation. They all can be defined as queues. In short, a place where entities are waiting for something to happen for some coherent reason. If you have a system and you have number of customers or number of entities are waiting to do some action or processing, then these entities are in ordered list, are in a queue. For a network example, a queue of packets usually stands in a router before they forward it to the distant address. The fifth term is creating. Creating causing the arrival of a new entity to the system at some point in time. Its dual process will be referred to as killing. Departure of a state. when you trying to create a simulation in a computer system, usually you need to create the arrival of new entities or customers for the system, and also creating a devastation or killing of the customers also can be distant or can be included in a creating process. And we have now scheduling. Scheduling is the act of assigning a new future event to an existing entity. Like a specific time, you need to change something, or you need a new assign a new entities or a new rush of entities in the system. You can schedule it ahead. We have random variable, and the variable you are familiar with. A random variable is a quantity that's uncertain. It's a variable, such as the arrival time between two incoming flights, or the number of defective parts in a shipment. Sometimes if you, for example, if you have a restaurant, the restaurant doesn't know when and how many customers they will have for the specific for a specific day if they don't have a reservations, for example. So the time a customer enters the restaurant is a random variable, and how much time the customer will spend in the restaurant is also another random variable. We have now random variate. Random variate is an artificially generated random variable. Sometimes in simulation we don't use sometimes we tend to use random variation that we can control the random variable, and we usually put processes based on calculations and system behaviors. Not all random variables are similar. We will discuss that later in the example. We have distribution. Distribution is a probabilistic term. Distribution is the mathematical law that governs the probabilistic feature of a random variable. We have, for example, Gaussian distribution. We have linear distribution. We have normal distribution. We have many distributions in mathematics. Now, these distributions are very important in simulations. Let's have an example that describes these terms with their associated terms in a description in the example. In this example, we are going to have an electric car battery charging station. We all know that electric cars are becoming more popular these days. So, for example, if you are going to build a charging station for this electric car, so say that this charging station has 5 rows, or it can accommodate 5 cars only at a time. This system can be described well by the following terminologies. Okay, we'll start with entities. What are the entities of such a system? The entities are of 3 types: cars, multiple instances. The charging stations are entity as well. The charging cord, like we say that there's 5 charging rows, so it means that there are 5 entities of charging stations, charging servers, sorry. And we have traffic generator, single instance, which creates cars and sends them to the battery charging station. Okay, the entity that generates the traffic for cars to be entered is also an entity. This and the traffic generator is actually it's a computer term, not it's a general term. In real life, we can't traffic generate car traffic unless if you say that okay, you will send cars to the charging station based on ad or some reservation or some scheduling. Okay, we have now states, variable states. The charging station has a server that's in either idle or free mode. Each car that's named not annotated by CI has a battery of some capacity Ki, the capacity of the car battery, and some amount of power Pi present within it. The traffic generator has parameters that specify the distribution of the random interaction times of cars. This is the example of battery charging station. Okay. These state variables are very important. If you are going to understand the system properly, you have to put the variables and understand the system and see what the variables are in the system. In this situation, we have three variables, like CR, the car battery, of some capacity, like 50 kilowatt or 25 kilowatt. The capacity that it's in the car, we all know that if you are going to charge to the charging station, you don't have to have zero kinetic energy or zero capacity. Usually you will have 25 or 20% the overall capacity of your battery when you are going to the charging station, and you have some power Pi present within it. The traffic generator job is to put the parameters for these randomly or based on the distribution. You are going to put these cars in a situation that they will visit the battery charging station. Now we will jump to events. One kind of event is the service car. Okay, the service car, when the car is serviced, the event of the car is serviced, it will get out of the server and another car will be entered. This is an event, which is an instruction to the server to charge the next car's battery. Another kind of event is arrival event, which is sent by the traffic generator to the charging station to inform that the car has arrived and it should be allocated for the any of the rows that's available to be charged. Finally, there is a create car event, which is sent by the traffic generator to itself to trigger the creation of a car. These are the three types of events we have in this battery charging station. The queue, we all know the queue is the cars queues in the front of the charging station. We say that the charging station has 5 rows. Since if we have 5 cars are charging at the same time, then we will have a queue outside the station. They are waiting for these 5 cars, any of them, to be charged and leave the station. So there will be some queue ahead of the charging station. Random realizations, variates. Car creation times is random. Car battery capacities are also random. Battery charge levels are also random. Sometimes when you are in a hurry, for example, if you are going to a gas station, and you don't need to put the full to put gasoline in a full tank. You must, based on your budget or your time to work, or you are in a hurry, for example. So if you have 25% of your battery and you went to the charging station and the charging becomes 75%, you will say, okay, this is enough for me for now, and you leave the station. So you don't have to fully charge. So the amount of battery charge levels is also a random realization. So you have the 3 random things here. The incoming time of cars is random realization. Each car has different battery capacity, and each car will have enough charge levels based on their situations. We can consider that as a service time. Some cars will stay in the server and the charging station for like 15 minutes. Some other cars will stay 90 minutes, for example. It's different. Based on these different things, you have to make a random variance or realization for these situations ahead in your programming. Okay, finally, with distribution, assume that uniform distributions for the car interaction times, battery capacity, and charging levels based on the statistics, of course. Okay, let's jump to the next topic we have here. We could performance evaluation techniques. We know that if you do a simulation, the most important thing you have to get results of this simulation. How you can measure these results? Okay, there are many techniques. Let's discuss it thoroughly. Modeling deals with the representation of interconnected subsystems and subprocesses with the eventual objective of obtaining an estimate of an aggregate systemic property or performance measure. The mechanism by which one can obtain this estimate efficiently and with confidence is the subject of performance evaluation. Okay, if we are going to do the simulation, we have to obtain a good estimate efficiently and with confidence. I mean by efficiently, like you can get, for example, if you are going to make a simulation for 100 years, you don't have to wait the computer program to last 100 years. The efficient result for this, because you are using simulation, you can speed up the operations within 100 years and make it maybe 1 month or less than that, and you will get the results with confidence about how this simulation has been performed. We have a term here that performance evaluation technique. Based off your simulation, you have to follow a specific PET or performance evaluation technique. This PET is a set of assumptions and analytical processes applied in the context of a simulation, whose purpose is the efficient estimation of some performance measure. PETs fall into two broad classes. You can either do direct measurement of your PET or by using modeling. These two broad classes actually are the most important things you get your results from a specific simulation. For the first type is direct measurement. The most obvious technique is to evaluate the performance of the system by directly measuring it. However, there are some limitations in existing available traffic measurements because of the following reasons. Not all simulations can undergo under direct measurements for some reasons. We have 3 reasons here why we can't get direct measurements. For example, the direct measurement of a system is only available with operational systems. So if you are going to make a machine or some big product, you have to finish it and put it under simulation or emulation and to get your results. Think that if you haven't done this system itself, it's just like in the under design, on the design or development stage, you can't get your direct measurements. Okay. The second thing, you can't do direct measurements of the system, because if you do that, you may affect the measured system while obtaining the required data. This may lead to false measurements of the systems. This usually happens in the laboratory. We all have passed electrical circuits lab. If you remember, if you are going to measure the resistance, for example, this resistance, it has some, of course, tolerance that it is not accurate. Okay, this you will probably use the color code to know what's the measurement, but the color code will not give you the exact resistance of this item. You will probably use a multimeter to do so. But think about this: the multimeter itself has a value, has a resistance itself. Internal, they call it internal resistance. So this multimeter is a resistant as well. If you put it in parallel with another resistance, you will get what? You will have 2 parallel resistors, and the value of this resistance will change a little bit. Assuming the multimeter internal resistance is very high, you can neglect it. But in some systems, even this negligible amount of of resistance measurement is important. So there is no ideal multimeter that has infinite resistance. No such circuits exist at all. Also, if you are going to measure the current in a load in a system, this is a battery, this is a bulb, and you have to put the multimeter or ammeter in series. Okay, assuming that if the multimeter is idle, is optimal, you have to have zero resistive here, so that the multimeter will not conduct any current. But since we don't have any real zero resistive, even these wires has its own resistive, so then part of the current will be consumed by the multimeter, not by the load. So for accurate measurements, specific direct measurements cannot be achieved in these systems. Okay, the third important reason that we can't use direct measurement is it might be not practical to measure directly the level of end-to-end performance sustained on all paths of the systems. Hence, to obtain the performance objectives, analytical models have to be set up to convert the raw measurements into meaningful performance measurements. Sometimes the direct measurements will not give you the exact picture of your system. You have to make some specific conversions or raw measurements to do so. For example, if you are in the lab and you are doing a direct measurement, maybe you are dealing with your temperature. You are in a room temperature, and the humidity is constant in the lab. But this resistor may be in a working circuit outdoors. The measurements will not be accurate because it has different environment. So sometimes systems, sensitive systems, you have to take into account that maybe this resistor will operate at 80 degrees centigrade, not in 20 degrees centigrade, and things may change as well. Okay. We actually discussed thoroughly why this direct measurement is not possible for all simulations. Now let's jump for modeling. So if we can't do direct measurements, we usually get our performance evaluation using modeling. During the design and development phases of a system, modeling can be used to estimate the performance measures to be obtained when the system is implemented. Modeling can be used to evaluate the performance of the working system. We all know modeling bases on mathematical models or some equations, so it usually gives you the results as theoretical results, not actual results. But it's sometimes the only choice we have before implementing a system, especially after the system undergoes some modifications. Modeling does not affect the measured system. This is a good thing, plus for modeling, as it does in the direct measurement technique, and can be used during the design phases. Even your system is not completed, but your modeling in the computer system is ready, and you can do measurements and everything you want to test the modeling system. However, modeling suffers from the following problems. As we have problems in direct measurements, modeling has all its own limitations as well. The problem of system abstraction. This may lead to analyzing a model that does not represent a real system under evaluation. We all know a simulated system in computer program is not exactly 100% than the real system outside the computer. So there is a problem of system abstraction here. Problems in representing the workload of the system. Okay, in the real system, workload can be changed based on many behaviors, many environmental options. We said previously that in simulation we will focus only on the important environment behavior to the system. We can't obtain all We can't include all the complex environment in the simulation, unless if you want it is very accurate. So there will be problems in representing all of the system. Thirdly, is problems in obtaining performance measure for the model on mapping the results back to the real systems. Sometimes, although there are some performance measures obtained, but when you do the real system, these performance measures may differ a little bit. But it's better to get these measurements before building the system, just to make an estimate. For this reason, they usually put the risk factor. What is a risk factor? For example, if you have a system that it's operating 100% under specific environmental behavior, you usually put a risk factor. A risk factor is like if you are using 1 for a risk factor, you will probably put 2.0 or 1.5 just in case anything happens in the real system. So if we will assure that you already put a risk factor for your system and it will work in the real design. After then, you can use optimization to reduce this risk factor to a minimum possible. Okay. Let's consider some practical considerations. Simulation is, in some sense, the act of pretending that one is dealing with a real object when actually one is working with an imitation of reality. It may be worthwhile to consider that when such pretense is warranted and benefits dangers of engaging it. We have a important question here is why do we use models? Actually, we have answered this before, but let's focus it again because this is for the it's important. Models reduce costs using different simplifying assumptions. For example, a spacecraft simulator can, on a certain computer or simulated system, is also a computer model of some aspects of the spacecraft. It shows on the computer screen the controls and functions that the spacecraft user is supposed to see when using a real spacecraft. To train individuals using a simulator is more convenient, safer, and cheaper than real spacecraft that usually cost billions of dollars. Okay, when to use simulations? Simulation is used in many situations, such as when the analytical model solution is not possible or feasible. In such cases, experts resort to simulations. Many times, simulation results are used to verify analytical solutions in order to make sure that the system is modeled correctly using analytical approaches. Dynamic systems, which involve randomness and change of state with time. An example of our electrical charging station, where cars come and go unprecedentedly to charge their batteries. In such systems, it's difficult, sometimes impossible, to predict exactly what time the next car should arrive at the station. So if you use a simulation, you will probably use a constant, or not constant, a good random variate to represent the number of cars coming into the station. But you can't use that in real life, because in real life you will build a station and wait for the cars, and things will be messed up. Okay, complex dynamic systems, which are so complex that when analyzed theoretically will require too many applications. In such cases, it is not possible to study the system, analyze it analytically. Therefore, simulation is the best approach to study the behavior of such a complex system. So, in short, these 4 points says that when system is analytically vague or analytically unavailable, it means that you don't have a specific mathematical equation that gives you the exact results. You will tend to use simulation. For example, if you have a simple equation like x equal 5 multiplied by y, then you have a definite, an exact analytical problem. But if you have a problem, you are dealing with a system, you don't have the equation for it. Everything is random. Its input, its output, its service time. you usually tend to use simulation and see the performance technique results for that. Okay, then how to simulate? This is the major thing we are going to study in this course. Suppose one is interested in studying the performance of an electric charge station, electric car charger station. The behavior of this system may be described graphically by plotting the number of cars at the charging station and the state of the system. Every time a car arrives, the graph increases by 1 unit, while a departing car causes the graph to drop 1 unit. This graph, also called a sample path, could be obtained from the observing of a real car charging station, but could also be constructed artificially. Such artificial construction and analysis of the resulting sample path or more sample path is in more complex cases constitutes a simulation process. Okay, so how to simulate? When you use simulate, you get results from simulation. You are not certain if these results are accurate or not. So if you are going to plot a real system, like you have a real implementation of a car's charging station, and you get the data from it, you will have a specific curve, and when you do simulation, your curve of your simulation should be similar somehow to the real system. In that case, your simulation will be perfect for another station, so you don't have to worry about how to get the perfect curve for that. For example, in your model exams, I usually follow a curve of a previously exams or paper exams. For example, last year we didn't have online exams. We used in class exams, and after like certain amount of points from students, I have curved, like some students they get higher grades, some other students medium grades, some students they have low grades. So I have a curve for that. So if I'm going to do an online exam on Moodle, the result should be similar. Like if I'm good in the designing the exam, then the curve should be similar somehow. Some exams we are doing here, because to avoid cheating, or the students usually not cooperate with their instructors, they like may cheat or they help each other. There will be certain ambiguity or deficiency in the curve. So if the curves are not similar for previous results, this means that the exam is not good enough. We have to repeat the exam, and so on. Okay, let's jump to the last equation. How to program a simulation. You have to build the flowchart for the simulation. Simulation may be performed manually on paper instance frequently. However, the simulation model is either a computer program or some kind of input simulation software. This simple flowchart tells you how to build a simulation. It's very simple. We will have a simple assignment for doing a simple simulation for a simple problem. You have to follow this flowchart to do it. Thank you for listening. If you have any question, don't hesitate to email me on Moodle. And if you have a broad question, we will make a discussion board on Moodle to do so. Thank you again.